Hello, and welcome to our last video of chapter 10. So this is on distances. It doesn't actually have a specific chapter in the book. We kind of pulled from a couple of chapters, so we don't really have a chapter number there. But let's go ahead and look at some distances. Okay, so first off, we're looking at the distance from a point to a line. And we have to be a bit more specific here, right? If we think about a point in space and a line in space, actually, the line is lots of distances away from that point. So when we say distance, we mean the place where the point is closest to the line, or that shortest distance. So that's labeled as h here on this diagram. And of course, that's the perpendicular distance, right? So the dashed line and the blue line there would have a right angle. And that gives us the shortest distance between the line and the point Q. And throughout this lecture, we'll think about sort of a general point on a line or a plane that we'll call P there. And of course, so doing that, by creating a right angle, we can use trigonometry. So h, that shortest distance, the thing we're actually interested in, is the magnitude of PQ times by the sine of that angle between them. Okay, so knowing that that's true, we can sort of copy that formula over here. And this looks quite similar to something we've seen before in terms of cross products. In fact, there it is. So if we take PQ cross D, some vector D, and we'll see that's in the direction of H. Well, PQ cross D is the magnitude of PQ, the magnitude of D times the sine of the angle between them. And we look, and that's almost what we have above there with the PQ and the sine. All we have to do is divide by the magnitude of that D, and we have exactly what we want. So that left-hand side there is exactly equal to h, and that is the formula we're going to use. Right, so we take PQ cross D, so the magnitude of that, divide by the magnitude of D, all of that together, which of course keep in mind is a number, right, that's a scalar. That will give us h, which is the distance we want. Okay, so having said that, let's go ahead and try an example. Okay, so we have PQ cross D, magnitude of that, divided by the magnitude of D. That's the formula we have there. We want to find the distance between the points. So the point is 113. And the line, right, so that's the line in space. It's in its vector form, 1, negative 1, 1. And then plus t, 2, 3, 1. So we have the point in the direction. And so just a reminder, this is kind of what our thing looks like. So first, we take a point on the line. Now, of course, there are lots of points on the line, but 1, negative 1, 1 seems like the most obvious one. And given the point on the line, we can find PQ, right, the vector that goes from P to Q. And keep in mind, right, that's a vector from P to Q, and we could think, well, can we not just use that distance? But of course, that's not the shortest distance from the point P to Q. And again, you'll see on the graph there, we've got D. D is the direction of the line. So really, we're going to have everything we need, right? We have PQ, 0, 2, 2. The direction of the line, well, that's simply 2, 3, 1. We have that from the equation of the line, from right here. And so everything we need, we have right there that we can plug into the formula for h. So we take the cross product of PQ and D, which is negative 4, 4, negative 4. We take the magnitude of that, and we take the magnitude of D itself. So the magnitude of the numerator is 4 root 3, the magnitude of the denominator is root 14, and that gives us altogether the distance, which is about 1.85. Okay, so I'll say each of these cases we have a kind of a formula, and once we've got that formula, we can plug in everything we need to do it. Okay, so our next example, we previously had it between a point and a line. Now we're going to look at the distance between two lines. And just as previously, if we think about two lines in space, there are lots of distances. So once again, we're looking for that shortest distance. It's a little hard to see here, but if you can kind of imagine that the blue lines are the two lines we're interested in, but they're not 2D, this is 3D, and so you can see the two right angles there, right? That's what the top right angle is kind of indicating, that these aren't necessarily pointing in the same direction. So again, if we're looking for the shortest distance between the two lines, then really what we're looking for is the point where the line that joins them up is at a right angle, is orthogonal to both of them. And so yeah, so you're sort of writing that again. So it's where h is perpendicular to both the two lines, at the top line and the bottom Okay, so let's consider the direction C. So the direction C, if we're going to say it's perpendicular to both, well, we find a vector that's perpendicular to two lines by taking the cross product of those two lines. So that direction C is the cross product of D1 and D2. And ultimately what we're trying to find is the projection of P1 and P2. Yeah, and we should go back and so P1 and P2 are 2 points. P1 is on the first line, P2 is on the second line. And so P1 to P2 is joining those up, but again, that's not necessarily the shortest distance. So to find the shortest distance, we want to project that onto this C vector, this shortest thing that's perpendicular to both of those lines. So we take the projection of P1, P2 onto C. We have the formula for projection right here. So you're going to take the dot product of P1, P2 with C. The denominator is the dot product of C with itself, or the magnitude of C squared. We times that by the direction of C, but then because we're looking for a distance, we find the magnitude of all of that together. We can play around with this just a tiny bit to simplify. Because we're inside a magnitude, we can take the magnitude of C here. But you can see we've got the magnitude of C here and the magnitude of C squared here, so we can just kind of cancel out. And so our final equation is P1, P2 dot C. You take the absolute value of that, right? So that's a scalar, so we don't need the magnitude symbols. We'll just take the absolute value if it's negative. And we divide that by the magnitude of C. And once again, we've got a formula that's really not too bad to find the shortest distance between two lines. And so to be clear what this is, the P1 is a point on the first line, the P2 is a point on the second line. The P1, P2 is a vector between those. And then the C is something perpendicular to both of those, which we found as the cross product. So again, let's leap into an example. We have the formula here. I've left the diagram up there so you can see what's happening. So we want to find the distance between two lines, and here are our two lines. So these are in parametric form. We've got the first line, x equals 1 plus 3t, etc. And then the second line, the x, the y, and the z there. So the very first thing we do, well, let's take 2 points, a point on each line. And again, there are infinitely made choices here, but there's a very obvious one for the first line. Just 1, 2, 0. The second line, negative 2, 3, 5. So that's the 2 points. Then we need the vector P1 to P2, which we find by subtracting. And then we also need the direction of the two lines. But again, that's very obvious. For the first line, it's 3, negative 1, 1. Second line, 4, 1, 2. And using the directions, the D1 and the D2 for each line, we can find the cross product of those to find the direction C, right? It's perpendicular to both. So we take the cross product of D1 with D2 and we get negative 3, negative 2, 7. And that is our direction C. And so finally, we need that projection that we talked about. So we're going back to using this formula here, the P1, P2 dot C, and the magnitude of C. So we take the dot product of C with P1, P2, and that comes to 42. We take the magnitude of C, which is of course just kind of 3 squared, 2 squared, 7 squared, square rooted. Find the ratio of those two things and divide, and we get 5.3 or so. Okay, and then our final case is going to be the distance between a point and a plane. Once again, as we've seen many times, this is going to be that shortest distance, so when Q is perpendicular to the plane. Okay, once again, the plane will have lots of distances from that point Q. We're looking for that shortest one. And so again, we're going to take a point P that's on the plane, the point Q that we're interested in. H is going to be that shortest distance, that perpendicular. And of course, N is the normal vector, right? N is the normal vector to the plane. And so we can take the projection of N onto this PQ. Sorry, excuse me, the projection of PQ onto this N gives us it into this kind of right angle perpendicular direction. Once again, if we take the projection formula right there, and actually this is going to look quite similar to the last case, right? We've got that N in there. We take the magnitude of that N, but then we've got the magnitude of N squared, so that kind of cancels. It actually gives us a pretty simple formula. So N is the normal vector. PQ is the vector from any point on the plane P to the point Q. And again, that's all we need. Once again, the numerator here is a scalar, so we just have the absolute value signs there. So let's go ahead and do it. So again, we've got the formula written up there. We want the distance between the point So that's the Q, 2, 1, 4. And there is our plane 2x minus 5y plus 6z equals 9. Keep in mind that we have the plane, we sort of automatically know the normal vector, right? The right angle vector there is 2, negative 5, 6. But then we do need a point on the plane. Okay, and there's infinitely many options, there's all kinds of things we can do. It's not quite as straightforward with the lines, but it's not too bad either. I think the easiest thing to do is think of a point on the plane, just take the x and the y to be 0 and see what the z should be. Also make our math pretty easy, I think. And so if we take the x to be 0 and the y to be 0, the z has to be 9 over 6, which is 1.5. So there is a point on the plane, and again I've kind of emphasized here that there's a point on the plane, there are lots of other ones. And if we have the a point on the plane, we can find the vector from P to Q. Okay, we have the point 2, 1, 4, so the vector from P to Q is 2, 1, 2.5. And again, once we've got those two things, there's nothing particularly hard about this. We take the dot product of n and PQ. So our normal vector is 2. Oh, I have a typo there. There should be 2, negative 5, 6. And the PQ is 2, 1, 2.5. And then we take the magnitude of the 2, negative 5, 6. And really we just, plug all that into the formulas and the things we've seen. So we get 14 over root 65. Again, I've taken the absolute value there. It's not negative as it turns out. But that gives us 1.74. So it tells us that the shortest distance between that point 2, 1, 4 and the plane 2x minus 5y plus 6 equals 9, that shortest distance is 1.74. Okay, so we've seen three possibilities, a point to a line to a line, and a point to a plane. And I guess that's about it. Thank you.